Hey guys, so for this fourth lesson from section 2.2, we're just looking at a last couple examples of just a few types of problems that you're going to run into. So we're going to look at this first one, and then I got one more for you on the back. So for this first one, we're looking at just looking for the equation of a parabola that passes through this point and is tangent to this line. So at this point, so I got some of that going for you over here on the graph. So here is the line that it is tangent to, and because it says that it passes through -4, -13, so we know that it's going to pass through this point right here, and we know it's going to touch this line because it's tangent to this line at 1, -3. So just as a little visual, the only type of parabola that would fit within that description would have to be a downward facing parabola, because it's got to run through this point and it's got to touch that line somewhere right about there. So this is about the look that we would get for the parabola that we're trying to find. Think of the just sort of general form of a parabola, right? It was going to look something like this. And so our goal is to come up with the values for A, for B, and for C, so that we can just fill them into that setup and get the equation of that parabola. So for this, it's going to take a couple solving of systems of equations, since we have multiple variables that we don't know. So we're going to start by just using some of the information that we're given up here. So because it is tangent to this line, that means the slope at that point would have to be the same slope at this line. So the slope of our parabola right there would have to also equal -8, right? And so because it hits the tangent line at this point, we know that when x is 1, my slope is -8. Okay, and so the derivative at 1, we know would have to equal -8. And so let me just kind of throw in the statement for this. So at y equals -8x plus 5, our parabola is tangent at x equals 1. Okay, so now that we got that, let's jump down to looking for this stuff right here. So let's come up with just a couple equations that we can start with. We do know 2 points that are both on the parabola that we're looking for, so we're just going to start with those. So I'm going to sub in my -4 for x and my -13 for y into our formula right here. So let's just start with what we're using. So if you look back on this, you'll know. So we're going to use our -4, -13, and our 1, -3. Since those guys are on the curve. Alright, so if we now plug in those values into our formula here, so we'll just start with this one. So I'm going to throw my -13 in there for y. And I'm going to replace all of my x's with -4. So it looks something like this. And let's do the same thing using 1, -3. So I'm going to plug -3 in for y. And let's plug in 1 for my x's. Those always clean up super nice. Alright, so we just have a sort of an initial system of equations. We won't be able to completely solve for all the variables yet because we got 3 unknowns here. However, if we subtract, so I'm just going to do my top equation minus my bottom equation. So if I do a little subtraction on this, we can at least eliminate the c's. So let's do -13 minus -3. And we got 16a minus a. And for the b's, I'm looking at -4b minus b, so -5b. And so there's kind of our first equation. So we're going to need one more equation to go with this one that also contains just a and b. So that's what we're shooting for on the next one, and this is where the derivative is going to come in to help us. If you look back at the original formula for this parabola, so what would the derivative of this function look like? So if I just go through the same power rule process to get the derivative of this function, so we're going to multiply 2 to the front, so it becomes 2ax to the first, and then I'm going to multiply 1 to the front, so 1bx, and then c is a constant, so that would go away. So we have this set up right here for the general derivative of our parabola, and we saw up above that where x is 1, we had a slope or a derivative of -8. So I can set this equal to -8 while plugging in a 1 for x. So this would just become 2a plus b. And now we have our two equations. We're going to solve that system. So let me bring the first one down right here. And let me bring this guy over. And if we wanted to solve this using elimination, I got to get some letters to match up here. So I did notice that everything in here is divisible by -5, so that's what I'm going to start with. So I'm going to divide the top one by -5. So it's going to come out to be 2 equals -3a plus b. And we'll just bring this guy down here. So now if I do another little subtraction step, I can see that my b's will cancel. So let's just do the top equation minus the bottom equation. So 2 minus -8 would be 10. -3 minus 2 would be -5a. My b's cancel. It's what we were hoping for. Divide this guy over, and now we know that -2 is our a value. So just looking at the general setup of our parabola here, we now know that our leading coefficient is -2. And we're just going to do a little back substitution here. So if you look back at the equation that we had right here, I could now take my -2 and plug it in for a. And so if we solve this one for b, we're going to come out with b is -4. So we now know our b value. And last one, now that we know a and b, we're going to take one of the equations from up top and replace a and b with those values. So a is going to be -2, b is -4, and we're solving for c. So if we do a little cleanup on that, we're going to get 3 for our c value. And then we have the equation of our parabola. So let me show you one last problem here. All right, so when you are asked to find rates of change, in other words, derivatives, with respect to different variables, remember, we're used to seeing this in terms of y and x, but it doesn't have to be y and x, it could be anything. And so for this one, this is just the formula for area of a circle. And so they're telling us the area of a circle is pi r squared. We know that r is the radius. And so if we want to find the rate of change of the area with respect to r, then in terms of just putting it into proper notation, we're going to say, let's take the derivative of a with respect to r. So it's just like we would do with y and x. If this was y equals something where x was on this side, we would have dy over dx. But just for proper notation, we're not dealing with y and x, we're dealing with a and r, and so we want to put it in those terms. And so the way we would read that is, again, the derivative of the area with respect to the radius. And so if we just kind of go through our normal process on this, right, our power rule, where you multiply 2 to the front, so it becomes 2 pi r to the first. This now is an expression that represents the rate of change for any radius of a circle. And so if I had a circle with a radius of 8, I could just simply plug that in. And now I have the instant rate of change for a radius of 8. So that's it for that one, nice and short.